Picture this, a world where the skies are filled with thick, sulfuric acid clouds, the surface is hot enough to melt lead, and the atmosphere spins faster than the planet itself. This isn't a scene from a sci-fi movie, this is Venus, Earth's so-called evil twin. Despite being similar in size and composition to our home planet, Venus is a place of extremes and enigmas that defy explanation. From its runaway greenhouse effect to its mysterious lightning and bizarre surface features, Venus holds secrets that have puzzled scientists for decades. In this video, we're diving into 25 of the most baffling mysteries of Venus, each one more intriguing than the last. Why does Venus, a planet so similar to Earth, look and behave so differently? What hidden forces are at work on this hostile world? And what can these mysteries teach us about the universe we live in? Stick around, because by the end of this journey, you'll see Venus in a whole new light, and you might just question everything you thought you knew about our solar system. Let's get started. Now, let's turn our attention to the first and perhaps most striking mystery of Venus, the runaway greenhouse effect. Imagine a planet where the heat is so intense that it could melt lead in seconds. That's Venus for you. The surface temperatures here soar to a staggering 870 degrees Fahrenheit, making it the hottest planet in our solar system, even hotter than Mercury, which sits closer to the Sun. But how did Venus become such a scorching inferno? The answer lies in its atmosphere, which is packed with carbon dioxide, a greenhouse gas that traps heat like a thick, suffocating blanket. Unlike Earth, where greenhouse gases are balanced and help maintain a livable climate, Venus's atmosphere has gone into overdrive. The carbon dioxide levels are so high that they've created a feedback loop, trapping more and more heat until the planet became the fiery furnace we see today. What's truly baffling to scientists is how Venus, often called Earth's twin due to its similar size and composition, ended up so drastically different. Both planets formed around the same time, roughly 4.6 billion years ago, and likely started with similar ingredients. Yet, while Earth developed oceans, a breathable atmosphere, and a stable climate, Venus spiraled into chaos. Some theories suggest that Venus may have once had water, just like Earth, but something triggered its greenhouse effect to spiral out of control. Was it a catastrophic event, like a massive volcanic eruption that released too much carbon dioxide? Or did Venus's proximity to the Sun play a role in evaporating its water and sealing its fate? These questions remain unanswered, leaving scientists to wonder how two planets with such similar beginnings could take such divergent paths. The runaway greenhouse effect on Venus isn't just a scientific curiosity, it's a cautionary tale. It shows us how delicate the balance of a planet's atmosphere can be and how easily it can tip into extremes. As we continue to study Venus, we're not just uncovering the secrets of our solar system's past, we're also gaining insights that could help us better understand and protect our own planet's future. And with that, we're ready to explore the next mystery, the strange and unexplained super-rotation of Venus's atmosphere. Now, let's dive into one of the most puzzling behaviors of Venus, its atmosphere's superrotation. Picture this: while Venus itself takes a sluggish 243 Earth days to complete a single rotation, its atmosphere races around the planet at an astonishing speed, completing a full rotation in just 4 Earth days. That's 60 times faster than the planet's surface. This bizarre mismatch between the atmosphere and the surface is unlike anything we see on Earth or any other planet in our solar system, and it has left scientists scratching their heads for decades. So, how does Venus's atmosphere manage to whip around so quickly? One leading theory suggests that the intense heat from the Sun, combined with Venus's thick carbon dioxide atmosphere, creates powerful winds that push the atmosphere forward. These winds, known as superrotational winds, could be driven by the planet's extreme temperature differences between its day and night sides. The sun heats the atmosphere on the day side, causing it to expand and rise, while the cooler night side contracts and sinks. This constant churning might generate enough momentum to keep the atmosphere spinning at such incredible speeds. Another intriguing idea points to Venus's lack of a global magnetic field. Without a magnetic field to shield it, the solar wind, a stream of charged particles from the sun, directly interacts with Venus's upper atmosphere. This interaction could transfer energy to the atmosphere, helping to accelerate its rotation. However, while these theories offer possible explanations, none fully account for the sheer speed and stability of Venus's superrotation. The phenomenon remains one of the planet's most enduring mysteries. What makes this even more fascinating is that Venus's superrotation isn't just a fleeting event, it's a persistent feature. Observations from missions like the European Space Agency's Venus Express have shown that this rapid atmospheric movement has been ongoing for decades, if not longer. Yet, despite decades of study, scientists still can't pinpoint exactly what keeps this atmospheric engine running. Is it a combination of factors like solar heating and atmospheric waves? Or is there something entirely different at play that we haven't discovered yet? This mystery isn't just about understanding Venus, it's about unraveling the complex dynamics of planetary atmospheres. By studying Venus's superrotation, scientists hope to gain insights into how atmospheres behave under extreme conditions, which could shed light on similar processes on exoplanets orbiting distant stars. And as we continue to explore this enigma, one thing is clear: Venus's atmosphere is a whirlwind of secrets, spinning faster than our understanding can keep up. With that, let's move on to another head-scratcher: the mystery of Venus's missing water. Where did it all go, and what clues does this vanishing act hold about the planet's past? Now, let's turn our attention to one of the most intriguing questions about Venus. Where did all its water go? Scientists believe that Venus may have once been a very different planet, possibly even home to vast oceans. But today, it's a dry, scorching wasteland. So, what happened to all that water? The answer lies in a combination of factors that transformed Venus into the arid world we see today. Evidence suggests that Venus might have had liquid water on its surface billions of years ago. This idea comes from studying the planet's atmosphere, which contains trace amounts of water vapor, as well as its surface features, which some scientists think could have been shaped by ancient oceans. But if Venus did have water, it didn't last. Over time, something caused the planet to lose its water, and the leading suspect is the Sun. Venus is closer to the Sun than Earth, and its lack of a protective magnetic field left it vulnerable to the Sun's powerful solar winds. These winds, made up of charged particles, could have stripped away Venus's water by breaking apart water molecules in the upper atmosphere and carrying the hydrogen atoms into space. But solar winds aren't the only culprit. Chemical reactions in Venus's atmosphere may have also played a role. The planet's thick carbon dioxide atmosphere creates a runaway greenhouse effect, trapping heat and raising surface temperatures to levels that would have boiled away any liquid water. As the water evaporated, it could have reacted with sulfur dioxide in the atmosphere, forming sulfuric acid clouds. Over time, these clouds may have rained down acid, further eroding the surface and locking away any remaining water in chemical compounds. Another theory points to Venus's slow rotation and lack of plate tectonics. Without the movement of tectonic plates, the planet couldn't recycle water and other materials back into its atmosphere, leaving it to slowly lose its water over billions of years. This combination of solar winds, chemical reactions, and geological inactivity paints a picture of a planet that once had the potential to support life, but ultimately lost its water to a series of cosmic and atmospheric events. The mystery of Venus's missing water isn't just about understanding the planet's past, it's also about what it means for other worlds. If Venus could lose its water, could the same happen to Earth? Or could this process explain why some exoplanets orbiting close to their stars are dry and barren? By unraveling the secrets of Venus's water loss, scientists hope to gain insights into the delicate balance that allows a planet to hold onto its water and potentially its habitability. With this mystery still swirling in our minds, let's shift gears to another enigmatic feature of Venus: its strange and unexplained lightning. What makes it so different from Earth's, and what clues does it hold about the planet's atmosphere? Now, let's dive into one of the most electrifying mysteries of Venus: its enigmatic lightning. Unlike the lightning we're familiar with on Earth, the lightning on Venus is a whole different beast, and scientists are still scratching their heads over how it forms and what it tells us about the planet's atmosphere. On Earth, lightning is typically caused by the collision of ice particles and water droplets in storm clouds, creating an electrical charge. But Venus doesn't have the same kind of weather systems. Its atmosphere is dominated by thick sulfuric acid clouds, and the temperatures are so extreme that water, as we know it, can't exist. So how does lightning even happen there? That's the million-dollar question. What makes Venusian lightning even more puzzling is that it behaves differently from Earth's. While Earth's lightning is concentrated in specific storm systems, Venus's lightning seems to be more widespread and frequent, occurring in bursts across the planet's atmosphere. Some scientists believe this could be due to the unique chemical makeup of Venus's clouds, which are rich in sulfuric acid and other compounds. These chemicals might create electrical charges in ways we don't fully understand yet. Another theory suggests that Venus's lightning could be linked to its volcanic activity. The planet is dotted with volcanoes, and some researchers think that volcanic eruptions might release particles into the atmosphere that trigger electrical discharges. However, this idea is still up for debate, as no direct evidence of active volcanism has been observed in recent times. What's even more intriguing is what this lightning reveals about Venus's atmosphere. The presence of lightning suggests that there's a lot of energy and turbulence in the planet's thick, swirling clouds. This could mean that Venus's atmosphere is far more dynamic and complex than we once thought. It also raises questions about how lightning interacts with the planet's runaway greenhouse effect and whether it plays a role in shaping the atmosphere over time. But here's the kicker: despite decades of observations, scientists still can't say for sure how Venusian lightning forms. Some spacecraft, like the European Space Agency's Venus Express, have detected signals that resemble lightning, but these findings are often indirect and open to interpretation. Without more direct measurements, the mystery remains unsolved. So, what does this mean for our understanding of Venus? The enigmatic lightning is a reminder that even a planet as seemingly hostile as Venus has secrets waiting to be uncovered. It challenges our assumptions about how lightning works and pushes us to rethink the processes that drive atmospheric activity on other worlds. With this electrifying mystery still sparking curiosity, let's turn our attention to another puzzling feature of Venus: the mysterious dark streaks in its atmosphere. What could these streaks be, and what do they tell us about the planet's hidden dynamics? Now, shifting our gaze to another baffling feature of Venus, we encounter the mysterious dark streaks that streak across its atmosphere. These enigmatic markings, often described as dark patches or streaks, have puzzled scientists for decades. Unlike the uniform haze of Venus's sulfuric acid clouds, these streaks stand out as irregular, shadowy patterns, raising questions about their origin and what they might reveal about the planet's hidden processes. One of the leading theories suggests that these dark streaks could be linked to volcanic activity. Venus is known to have a history of intense volcanic eruptions, and some researchers believe that these streaks might be the result of volcanic ash or other particles being ejected into the atmosphere. If active volcanoes are still present on Venus, they could be releasing materials that create these dark patterns as they mix with the planet's thick clouds. However, this theory is still speculative, as no definitive evidence of ongoing volcanic activity has been observed. Another intriguing possibility is that these streaks could be evidence of microbial life. While it might sound like science fiction, some scientists have proposed that microorganisms could exist in Venus's upper atmosphere, where conditions are less extreme than on the surface. These microbes, if they exist, might produce chemical compounds that could darken the clouds, creating the streaks we observe. This idea is supported by the discovery of phosphine gas in Venus's atmosphere, which some researchers believe could be a potential biosignature. However, this theory remains highly controversial and requires much more evidence to be taken seriously. What makes these dark streaks even more perplexing is their transient nature. They appear and disappear over time, suggesting that whatever causes them is dynamic and possibly tied to the planet's atmospheric processes. Some scientists think that these streaks could be the result of chemical reactions occurring within the clouds, perhaps involving sulfur compounds or other elements unique to Venus's atmosphere. These reactions might create dark particles that temporarily alter the appearance of the clouds before dissipating. Despite the many theories, the true nature of these dark streaks remains a mystery. Observations from spacecraft like the European Space Agency's Venus Express and Japan's Akatsuki have provided valuable data, but the streaks are difficult to study in detail due to the planet's thick cloud cover and the challenges of observing Venus from Earth. Without more direct measurements or close-up observations, scientists can only speculate about their origin. So, what do these dark streaks tell us about Venus? They serve as a reminder that even a planet as seemingly inhospitable as Venus holds secrets that challenge our understanding. Whether they're the result of volcanic activity, microbial life, or some other process entirely, these streaks highlight the complexity of Venus's atmosphere and the need for further exploration. As we continue to unravel the mysteries of Venus, let's turn our attention to another puzzling aspect of the planet, the absence of plate tectonics. Why does Venus lack this geological process, and what does it mean for the planet's surface and interior? Now, let's dive into one of the most striking differences between Venus and Earth, the absence of plate tectonics. While Earth's surface is divided into moving plates that constantly reshape the planet, Venus seems to lack this dynamic process entirely. This raises a fascinating question. Why doesn't Venus have plate tectonics, and what does this mean for its geology? On Earth, plate tectonics play a crucial role in shaping the planet's surface. They drive the formation of mountains, trigger earthquakes, and even recycle materials through processes like subduction. But Venus, despite being similar in size and composition to Earth, appears to have a rigid outer shell. Instead of moving plates, its surface seems to behave more like a single, unbroken lid. This lack of tectonic activity has profound implications for how Venus's surface evolves over time. One possible explanation for this difference lies in Venus's extreme surface conditions. The planet's scorching temperatures, which can reach up to 900 degrees Fahrenheit, may prevent the crust from cracking and moving in the same way Earth's does. On Earth, water acts as a lubricant, helping plates slide past one another, but Venus is bone dry with no liquid water to facilitate this process. Without this lubrication, the planet's crust may simply be too stiff to break into moving plates. Another factor could be Venus's internal heat distribution. Earth's mantle convection drives plate tectonics, but Venus's mantle might behave differently. Some scientists believe that Venus's interior heats up and cools down in cycles, leading to periods of intense volcanic activity followed by long stretches of geological calm. During these active phases, massive outpourings of lava could resurface large portions of the planet, effectively resetting its crust and preventing the formation of tectonic plates. The absence of plate tectonics also has a significant impact on Venus's surface features. Without the constant movement and recycling of crust, Venus's surface is dominated by vast volcanic plains, towering shield volcanoes, and unique structures like coronae and tesserae. These features suggest that Venus's geology is shaped more by vertical forces like mantle plumes pushing up from below, rather than the horizontal movements seen on Earth. But what does this mean for Venus's internal heat? Without plate tectonics to release heat from the planet's interior, Venus might store more of its energy internally. This could explain why the planet experiences such extreme volcanic activity during its active phases. Some researchers even speculate that Venus might undergo catastrophic resurfacing events, where the entire surface is flooded with lava in a relatively short period of time. The mystery of Venus's missing plate tectonics challenges our understanding of how rocky planets evolve. It forces us to reconsider the factors that drive geological activity and how different conditions can lead to vastly different outcomes. As we continue to study Venus, this puzzle reminds us that even planets with similar origins can take wildly divergent paths. With this in mind, let's turn our attention to another unique feature of Venus, the strange flat-topped volcanoes known as pancake domes. What makes these formations so different from Earth's volcanoes, and what do they tell us about Venus's volcanic history? Now, shifting our focus to another intriguing feature of Venus, we encounter the peculiar pancake domes. These flat-topped volcanoes are unlike anything we see on Earth, and their unique shape has puzzled scientists for decades. So, what exactly are pancake domes, and how do they form on a planet as extreme as Venus? Pancake domes are broad, circular volcanic structures with flat tops and steep sides resembling, you guessed it, pancakes. They can stretch up to several miles across and rise hundreds of feet high. Unlike Earth's towering, cone-shaped volcanoes, pancake domes are much wider and flatter, a result of the unique conditions on Venus. The key to their formation lies in Venus's thick, dense atmosphere and its scorching surface temperatures. When lava erupts on Venus, it doesn't flow as freely as it does on Earth. Instead, the planet's high atmospheric pressure and extreme heat cause the lava to cool and solidify much more quickly. This rapid cooling creates a thick, viscous lava that spreads out in all directions, forming the wide, flat shape of the pancake domes. Another factor is the composition of Venus's lava. Scientists believe that the lava on Venus is richer in silica compared to Earth's basaltic lava. Silica-rich lava is stickier and less fluid, which further contributes to the dome-like shape. On Earth, silica-rich lava tends to form steep-sided domes, but on Venus, the combination of high pressure and rapid cooling flattens these structures into their distinctive pancake form. The presence of pancake domes also tells us something important about Venus's volcanic activity. Unlike Earth, where volcanic eruptions are often explosive and dramatic, Venus's eruptions are likely slower and more subdued. The lava oozes out gradually, spreading across the surface rather than building up into towering peaks. This suggests that Venus's volcanic processes are driven by different mechanisms, possibly linked to the planet's internal heat distribution and lack of plate tectonics. Interestingly, pancake domes are often found in clusters, hinting at regions of concentrated volcanic activity. Some scientists speculate that these areas might be hotspots where mantle plumes rise to the surface, fueling repeated eruptions over time. This could mean that Venus's volcanic activity is more localized than Earth's, with certain regions experiencing intense volcanic activity while others remain relatively quiet. The study of pancake domes not only sheds light on Venus's geology, but also challenges our understanding of volcanic processes in general. By comparing these formations to Earth's volcanoes, scientists can explore how different planetary conditions like atmospheric pressure, temperature, and lava composition shape the way volcanoes form and behave. As we continue to unravel the mysteries of Venus's pancake domes, they serve as a reminder of how diverse and complex planetary geology can be. Next, we'll explore another fascinating feature of Venus, the highly deformed tesserae terrain, which resembles crumpled paper and holds clues to the planet's ancient past. Now, let's turn our attention to one of Venus's most enigmatic features, the mysterious tesserae terrain. These regions, which cover vast areas of the planet's surface, are unlike anything found on Earth. Imagine crumpling a piece of paper into a tight ball, then flattening it out again. That's what the tesserae terrain looks like, a chaotic, highly deformed landscape of ridges, valleys, and fractures that stretch for hundreds of miles. But what caused this bizarre terrain, and what does it tell us about Venus's past? The tesserae regions are some of the oldest geological features on Venus, dating back billions of years. Their complex, jumbled appearance suggests that they were shaped by intense tectonic forces, possibly driven by the planet's internal heat and pressure. Unlike Earth, where plate tectonics continuously reshape the surface, Venus lacks moving plates. Instead, scientists believe that the tesserae terrain formed through a process called crustal shortening, where the planet's crust was compressed and folded, creating the crumpled, ridge-like structures we see today. One leading theory is that the tesserae regions were once part of Venus's ancient crust, formed during a time when the planet's surface was much more dynamic. Some researchers suggest that these areas could have been the sites of ancient mountain-building events, where massive forces pushed the crust upward, creating towering peaks and deep valleys. Over time, erosion and volcanic activity may have smoothed out some of these features, but the tesserae terrain remains as a testament to Venus's turbulent geological history. Another intriguing possibility is that the tesserae regions were shaped by a combination of volcanic and tectonic activity. Venus's surface is dotted with volcanoes, and some scientists believe that the tesserae terrain could have formed when lava flows interacted with the planet's crust, causing it to buckle and fold. This process, known as volcanic loading, occurs when the weight of volcanic material causes the crust to deform, creating the ridges and valleys characteristic of the tesserae terrain. The tesserae regions also hold clues about Venus's climate history. Some researchers speculate that these areas could have once been covered by oceans or lakes, which later evaporated as the planet's surface temperatures soared. The deformation of the crust could have been influenced by the presence of water, which would have made the surface more malleable and prone to folding. While this theory is still debated, it raises fascinating questions about whether Venus was once a more Earth-like planet, with liquid water and a potentially habitable environment. Studying the tesserae terrain is no easy task, as Venus's thick atmosphere and extreme surface conditions make it difficult to gather detailed data. However, missions like NASA's Magellan spacecraft have provided valuable insights, revealing the intricate patterns and structures of these regions. By analyzing this data, scientists hope to uncover more about the processes that shaped Venus's surface and how they differ from those on Earth. As we piece together the story of the tesserae terrain, it becomes clear that Venus's geological history is far more complex than we once thought. These crumpled landscapes are a window into the planet's ancient past, offering clues about its formation, evolution, and the forces that continue to shape it today. Next, we'll delve into another captivating mystery, the unexplained brightness of Venus's surface, which makes it one of the most luminous objects in our night sky. Now, shifting our gaze to another striking feature of Venus, let's explore the mystery behind its extraordinary brightness. Venus is not just a planet, it's a beacon in the night sky, often outshining every other celestial body except the Moon. But what makes Venus so dazzling? The answer lies in a combination of its thick atmosphere and unique surface composition. Venus's atmosphere is a dense blanket of carbon dioxide and sulfuric acid clouds which act like a giant mirror. These clouds are incredibly reflective, bouncing back a significant amount of sunlight into space. In fact, Venus reflects about 70% of the sunlight that hits it, a property known as its albedo. This high reflectivity is one of the key reasons Venus shines so brightly, even from millions of miles away. But the atmosphere isn't the only factor at play. Venus's surface also plays a crucial role in its brightness. The planet is covered in vast plains of volcanic rock, which are rich in minerals like pyrite and other metallic compounds. These materials have a natural sheen, further enhancing Venus's ability to reflect light. Some scientists even speculate that the surface might be coated with a thin layer of metallic frost, formed by chemical reactions between the atmosphere and the rocky terrain. This frost could act like a natural mirror, amplifying the planet's glow. Interestingly, Venus's brightness isn't constant. Observations have shown that its reflectivity varies slightly over time, hinting at changes in its atmosphere or surface. For instance, volcanic eruptions on Venus could release fresh layers of reflective material into the atmosphere, temporarily increasing its brightness. Similarly, shifts in cloud composition or atmospheric dynamics might also play a role in these fluctuations. The study of Venus's brightness isn't just about solving a planetary mystery, it also has broader implications for understanding other worlds. By analyzing how Venus reflects light, scientists can develop better models for studying exoplanets, especially those with thick, cloudy atmospheres. Venus serves as a natural laboratory, helping us refine our techniques for detecting and characterizing distant worlds. As we continue to unravel the secrets of Venus's brilliance, one thing is clear. This planet is a master of light, using its atmosphere and surface to create a spectacle that has captivated humanity for centuries. Next, we'll turn our attention to another puzzling aspect of Venus, the mystery of its missing magnetic field, and what it tells us about the planet's interior. Now, let's delve into one of the most perplexing aspects of Venus, the mystery of its missing magnetic field. Unlike Earth, which boasts a strong global magnetic field generated by its molten iron core, Venus seems to lack this protective shield. This absence raises critical questions about the planet's interior and its ability to safeguard its atmosphere from the harsh conditions of space. Earth's magnetic field is created by a process called the dynamo effect, where the movement of molten iron in its outer core generates electric currents, producing a magnetic field. Venus, however, doesn't appear to have an active dynamo. One leading theory suggests that Venus's core might have cooled and solidified over time, halting the dynamo process. Without this internal engine, Venus is left without a global magnetic field, leaving its atmosphere vulnerable to the relentless bombardment of solar winds. But the story doesn't end there. While Venus lacks a global magnetic field, it does exhibit weak magnetic anomalies, localized patches of magnetism scattered across its surface. These anomalies are thought to be remnants of a past magnetic field, or the result of interactions between the solar wind and Venus's upper atmosphere. Some scientists propose that these weak magnetic regions could be linked to ancient volcanic activity, which may have temporarily magnetized parts of the planet's crust. The absence of a global magnetic field has profound implications for Venus's atmosphere. Without this protective barrier, solar winds can strip away atmospheric particles over time, contributing to the planet's harsh, inhospitable environment. This process, known as atmospheric erosion, may explain why Venus has lost much of its water and why its atmosphere is dominated by carbon dioxide and sulfuric acid clouds. Interestingly, studying Venus's magnetic anomalies could provide clues about its geological history. If these weak magnetic regions are indeed tied to past volcanic activity, they might offer insights into the planet's internal dynamics and whether it was once more geologically active than it is today. Additionally, understanding why Venus lacks a global magnetic field could help scientists refine their models of planetary formation and evolution, shedding light on why Earth developed such a robust magnetic shield while Venus did not. As we piece together the puzzle of Venus's magnetic field, we're reminded of how much there is still to learn about this enigmatic planet. Next, we'll explore another fascinating mystery, the strange double vortex storms swirling at Venus's poles and what they reveal about the planet's atmospheric dynamics. Now, shifting our gaze to the poles of Venus, we encounter one of the most visually striking and scientifically puzzling features of the planet, the strange double vortex storms. Unlike Earth, which has a single, relatively stable polar vortex at each pole, Venus boasts a pair of swirling, hurricane-like storms at both its north and south poles. These vortices are massive, stretching hundreds of kilometers across, and their peculiar double-lobed structure has left scientists scratching their heads for decades. So, what exactly causes these double vortices? The answer lies in Venus's super-rotating atmosphere, which we discussed earlier. As the atmosphere whips around the planet at incredible speeds, it creates complex wind patterns that converge at the poles. This convergence forces the air to spiral downward, forming the distinctive double vortex. The exact mechanics of how these vortices maintain their shape and stability, however, remain a mystery. Some researchers suggest that the interaction between the planet's fast-moving atmosphere and its slow surface rotation plays a key role, while others point to the unique chemistry of Venus's atmosphere as a contributing factor. What makes these vortices even more intriguing is how they differ from Earth's polar vortices. On Earth, polar vortices are driven by temperature differences between the equator and the poles, and they tend to weaken or strengthen with the seasons. Venus, on the other hand, has no seasons due to its minimal axial tilt, and its vortices appear to be permanent fixtures. Additionally, while Earth's vortices are relatively calm and stable, Venus's double vortices are dynamic and ever-changing, with their shapes and intensities fluctuating over time. One of the most baffling aspects of these storms is their double-lobed structure. Why two vortices instead of one? Some theories propose that the shape is a result of the way Venus's atmosphere circulates, with the super-rotation creating a balance of forces that splits the vortex into two. Others speculate that the planet's topography or internal heat distribution might influence the formation of these twin storms. Despite decades of observation, no single explanation has fully accounted for this phenomenon. Studying these double vortices isn't just about solving a planetary puzzle, it's also about understanding the broader dynamics of atmospheric systems. By comparing Venus's vortices to those on Earth and other planets, scientists can gain insights into how different factors such as rotation speed, atmospheric composition, and planetary heat shape weather patterns across the solar system. This knowledge could even help us better predict and understand extreme weather events on Earth. As we continue to unravel the secrets of Venus's double vortices, we're reminded of how much this enigmatic planet has to teach us. Next, we'll turn our attention to another mysterious phenomenon, the rare and elusive ashen light that has puzzled astronomers for centuries. What could be causing this faint glow on Venus's night side? Let's find out. Now, let's turn our attention to one of the most elusive and mysterious phenomena ever observed on Venus, the enigmatic ashen light. For centuries, astronomers have reported seeing a faint, ghostly glow on the night side of Venus, a phenomenon that defies easy explanation. This eerie light, often described as a soft, ashen hue, has sparked countless theories and debates, yet its true cause remains shrouded in mystery. So, what exactly is the ashen light? Unlike the bright, reflective clouds that dominate Venus's day side, this faint glow appears on the planet's night side, where sunlight is completely absent. It's been compared to the faint glow of Earth's moonlit nights, but Venus has no moon, and its thick atmosphere blocks most starlight. This raises the question, what could possibly be illuminating the night side of this scorching, cloud-covered world? One leading theory suggests that the ashen light might be caused by chemical reactions in Venus's atmosphere. The planet's dense, sulfuric acid clouds are known to produce intense electrical activity, including lightning. Some scientists speculate that this electrical energy could excite atmospheric particles, causing them to emit a faint glow. This phenomenon, known as airglow, occurs on Earth as well, but Venus's unique atmospheric composition might amplify it, creating the ashen light we observe. Another intriguing possibility is that volcanic activity could be responsible. Venus is thought to have active volcanoes, and eruptions could release gases or particles that interact with the atmosphere, producing a faint glow. If true, this would not only explain the ashen light, but also provide evidence that Venus is still geologically active, a tantalizing prospect for planetary scientists. However, not all researchers are convinced by these explanations. Some argue that the ashen light could be an optical illusion, caused by the way our eyes or telescopes process the faint light reflected from Venus's day side. Others suggest that it might be linked to the planet's mysterious dark streaks or other atmospheric phenomena we've yet to fully understand. Despite decades of observation, no single theory has been able to fully account for this puzzling glow. The ashen light isn't just a scientific curiosity, it's a reminder of how much we still have to learn about Venus. Each time this faint glow is observed, it challenges our understanding of the planet's atmosphere, geology, and even its potential for harboring life. As we continue to study this phenomenon, we're reminded that Venus, despite its harsh conditions, holds secrets that could reshape our understanding of planetary science. With the ashen light still casting its mysterious glow, let's move on to another baffling feature of Venus: the thick, sulfuric acid clouds that shroud the planet. What role do these clouds play in Venus's extreme climate, and why do they remain such a focus of scientific study? Let's dive in. Now, let's shift our focus to one of the most defining features of Venus: its thick, sulfuric acid clouds. These clouds aren't just a striking visual characteristic. They play a crucial role in shaping the planet's extreme climate and remain one of the most studied aspects of Venus's atmosphere. But what exactly makes these clouds so unique, and why do they continue to captivate scientists? The sulfuric acid clouds of Venus are unlike anything found on Earth. They form when sulfur dioxide, a gas released by volcanic activity, reacts with water vapor in the planet's atmosphere. This chemical reaction produces tiny droplets of sulfuric acid, which then condense into thick, reflective clouds. These clouds are so dense that they completely shroud the planet, hiding its surface from view and giving Venus its bright, almost glowing appearance in our night sky. But these clouds do more than just obscure the surface. They're a key driver of Venus's runaway greenhouse effect. The sulfuric acid droplets reflect a significant amount of sunlight back into space, which might seem like it would cool the planet. However, they also trap heat, contributing to the planet's scorching surface temperatures. This dual role makes the clouds a critical factor in understanding why Venus is so much hotter than Earth, despite being similar in size and distance from the Sun. Another fascinating aspect of these clouds is their layered structure. Venus's atmosphere is divided into multiple cloud layers, each with its own unique properties. The upper clouds, for example, are where the sulfuric acid droplets are most concentrated, while the lower layers contain larger particles and even traces of other compounds. This complex structure creates a dynamic environment, with winds that whip around the planet at incredible speeds, further complicating our understanding of Venus's climate. Scientists are particularly intrigued by the possibility that these clouds could harbor microbial life. While the idea might sound far-fetched, some researchers have proposed that certain microorganisms could survive in the upper cloud layers, where temperatures and pressures are more moderate compared to the surface. This hypothesis adds another layer of mystery to the sulfuric acid clouds, making them not just a subject of atmospheric study, but also a potential window into extraterrestrial life. Despite decades of research, many questions about these clouds remain unanswered. How do they maintain their composition over time? What role do volcanic eruptions play in replenishing the sulfur dioxide needed to form them? And could they really be home to life? These questions keep scientists coming back to Venus, eager to unravel the secrets hidden within its acidic shroud. As we continue to explore the mysteries of Venus's sulfuric acid clouds, we're reminded of how much there is still to learn about this enigmatic planet. These clouds are more than just a barrier to the surface, they're a gateway to understanding the complex interplay of chemistry, climate, and even the potential for life in our solar system. With that in mind, let's turn our attention to another puzzling feature of Venus, the massive Y-shaped cloud patterns that dominate its atmosphere. What causes these strange formations, and what do they tell us about the planet's weather systems? Let's find out. Now, let's dive into one of the most visually striking mysteries of Venus, the massive Y-shaped cloud patterns that stretch across its atmosphere. These enormous formations, often spanning thousands of kilometers, are unlike anything seen on Earth or any other planet in our solar system. But what exactly are these Y-shaped clouds, and why do they hold such a prominent place in Venus's atmosphere? The Y-shaped cloud patterns are primarily observed in the upper layers of Venus's sulfuric acid clouds, where they appear as vast, dark streaks against the planet's bright, reflective atmosphere. These patterns are not static. They move across the planet, driven by the super-rotation of Venus's atmosphere, which whips around the planet at speeds up to 60 times faster than its surface rotates. This rapid movement creates a dynamic and ever-changing canvas, with the Y shape forming and reforming over time. One of the leading theories about these patterns is that they are the result of atmospheric waves, known as gravity waves or Kelvin waves, propagating through Venus's thick atmosphere. These waves are thought to be generated by the interaction between the planet's surface and its atmosphere, possibly triggered by Venus's rugged terrain or volcanic activity. As these waves travel upward, they distort the cloud layers, creating the distinctive Y shape that we observe from space. Another intriguing aspect of these patterns is their persistence. Unlike weather systems on Earth, which can change dramatically over short periods, the Y-shaped clouds on Venus can last for weeks or even months. This longevity has puzzled scientists, as it suggests a level of stability in Venus's atmosphere that contrasts sharply with the planet's otherwise chaotic and extreme conditions. Some researchers believe that the Y shape is maintained by a delicate balance between the planet's atmospheric circulation and the forces driving the waves, creating a kind of atmospheric equilibrium. The Y-shaped clouds also play a significant role in Venus's climate. They act as a kind of atmospheric barrier, influencing how heat and energy are distributed across the planet. By studying these patterns, scientists hope to gain insights into the broader dynamics of Venus's atmosphere, including how it maintains its super-rotation and why its climate is so different from Earth's. Despite decades of observation, many questions about these enigmatic clouds remain unanswered. What exactly triggers the formation of the Y shape? Why do these patterns persist for so long? And what role do they play in Venus's overall weather system? These questions highlight just how much we still have to learn about Venus's atmosphere and the forces that shape it. As we continue to explore the mysteries of Venus, the Y-shaped cloud patterns serve as a reminder of the planet's complexity and the challenges of understanding its unique environment. With that in mind, let's turn our attention to another puzzling feature of Venus, the planet's unusually slow rotation. What causes Venus to spin so slowly, and how does this affect its climate and geology? Let's find out. Now, shifting our gaze to another fascinating aspect of Venus, let's explore the mystery of its incredibly slow rotation. Unlike most planets in our solar system, Venus takes a staggering 243 Earth days to complete just one rotation on its axis. To put that into perspective, a single day on Venus is longer than its entire year, which lasts only about 225 Earth days. But what could cause a planet to spin so slowly, and what does this mean for its climate and geology? One of the most striking features of Venus's rotation is that it's not just slow, it's also retrograde. This means that Venus spins in the opposite direction to most planets, including Earth. If you were standing on Venus, the sun would rise in the west and set in the east, a complete reversal of what we experience here. Scientists have long puzzled over how Venus ended up with such an unusual rotation. One leading theory suggests that a massive collision with another celestial body billions of years ago could have flipped Venus's rotation, essentially putting it in reverse. Another possibility is that gravitational interactions with the Sun and other planets gradually altered its spin over time. The slow rotation has profound effects on Venus's climate. On Earth, our relatively fast rotation helps distribute heat evenly across the planet, creating distinct day and night cycles that moderate temperatures. But on Venus, the sluggish spin means that one side of the planet is exposed to the Sun's intense heat for an extended period, while the other side remains in prolonged darkness. This imbalance contributes to the planet's extreme surface temperatures, which can reach up to 900 degrees Fahrenheit, hot enough to melt lead. The slow rotation also affects Venus's atmosphere, contributing to the super-rotation phenomenon we discussed earlier, where the atmosphere whips around the planet much faster than the surface rotates. Another intriguing aspect of Venus's slow rotation is its impact on the planet's geology. Without the stabilizing force of a faster spin, Venus lacks the same kind of tectonic activity we see on Earth. Instead, its surface is dominated by vast volcanic plains and unique geological features like the pancake domes and tesserae terrain we've already explored. The slow rotation may also play a role in the planet's lack of a global magnetic field, as the sluggish movement of its core could hinder the generation of magnetic forces. Despite decades of study, the mystery of Venus's slow rotation remains unsolved. Was it always this way, or did something dramatic alter its spin? How does this slow rotation interact with other factors, like its thick atmosphere and extreme greenhouse effect, to shape the planet we see today? These questions continue to challenge scientists and highlight just how unique Venus is in our solar system. As we unravel the secrets of Venus's slow rotation, we're reminded of the delicate balance that governs planetary behavior. Next, we'll turn our attention to another puzzling feature of Venus, the unexplained hotspots scattered across its surface. What causes these areas to emit more heat than their surroundings, and what do they tell us about the planet's interior? Let's dive in. Now, let's turn our attention to one of the most intriguing features of Venus, its mysterious hotspots. Scattered across the planet's surface, these areas emit significantly more heat than their surroundings, creating a puzzle that has left scientists scratching their heads. What could be causing these localized bursts of heat, and what do they reveal about the inner workings of this enigmatic planet? One of the leading theories points to volcanic activity. Venus is known for its vast volcanic plains and unique geological features, like the pancake domes we've already explored. Some researchers believe that these hotspots could be evidence of active volcanoes, still erupting beneath the planet's thick atmosphere. If true, this would suggest that Venus is far from geologically dead, with molten rock churning beneath its surface and occasionally breaking through to release heat. However, detecting active volcanism on Venus is no easy task given the planet's dense clouds and extreme surface conditions. Another possibility is that these hotspots are linked to tectonic processes. While Venus lacks the plate tectonics we see on Earth, it does have massive rift zones and other geological structures that indicate some form of internal movement. These processes could generate heat as the planet's crust shifts and fractures, creating localized areas of increased temperature. Some scientists even speculate that Venus might have a form of squishy tectonics, where the crust behaves more like a thick, malleable layer rather than rigid plates, leading to unique heat distribution patterns. Interestingly, these hotspots aren't just random, they often appear in clusters, suggesting a deeper connection to Venus's internal dynamics. For example, some of the hottest areas are found near the planet's massive coronae, circular structures that resemble giant bullseyes. These features are thought to be the result of upwelling magma from Venus's mantle, which could explain why the surrounding areas are so much warmer. But without direct observations, it's difficult to confirm whether these hotspots are truly linked to volcanic or tectonic activity, or if something entirely different is at play. The mystery of Venus's hotspots also raises questions about the planet's overall heat distribution. Unlike Earth, where heat is relatively evenly spread due to our planet's fast rotation and active plate tectonics, Venus's slow spin and lack of tectonic movement could lead to uneven heat retention. This might explain why certain areas remain hotter than others, even as the planet's thick atmosphere works to trap heat globally. But again, this is just one piece of a much larger puzzle. As we continue to study these hotspots, we're reminded of how much we still have to learn about Venus. Are they evidence of a geologically active world, or do they point to processes we've yet to understand? Each discovery brings us closer to unraveling the secrets of this mysterious planet, but for now, the hotspots remain one of its most compelling enigmas. With this mystery still simmering, let's shift our focus to another fascinating feature of Venus, the circular coronae that dot its surface. What are these strange structures, and what do they tell us about the planet's interior? Stay with us as we explore this next piece of the Venus puzzle. Now, let's dive into one of Venus's most striking geological features, the enigmatic coronae. These circular structures, often resembling giant bullseyes, are scattered across the planet's surface and have puzzled scientists for decades. What exactly are these formations, and what clues do they hold about Venus's hidden interior? Coronae are thought to be the result of upwelling magma from Venus's mantle. Imagine a massive bubble of molten rock rising toward the surface, pushing the crust upward and creating a circular uplift. Over time, as the magma cools and retreats, the surface collapses, leaving behind a ring-like structure with a central depression. This process, known as mantle plume activity, is similar to what happens on Earth in places like Hawaii, where volcanic islands form over hotspots. However, Venus's coronae are far larger and more complex, with some spanning hundreds of kilometers in diameter. But not all coronae are created equal. Some are surrounded by concentric ridges and fractures, while others have smooth, flat interiors. This variety suggests that the processes forming these structures might differ depending on the region or the depth of the magma source. For instance, some coronae might form when the crust is thin and easily deformed, while others could result from more intense volcanic activity that reshapes the surface dramatically. One of the most intriguing aspects of coronae is their connection to Venus's internal heat. Many of these structures are found near areas of high volcanic activity, including the mysterious hotspots we discussed earlier. This has led scientists to speculate that coronae might be windows into Venus's interior, offering clues about how heat is distributed and released across the planet. If coronae are indeed linked to mantle plumes, they could provide valuable insights into Venus's geological activity and whether the planet is still volcanically active today. However, coronae aren't just about heat, they also reveal something about Venus's crust. The way these structures deform the surface suggests that Venus's crust might be more flexible than Earth's, bending and cracking under pressure rather than breaking into rigid plates. This squishy behavior could explain why Venus lacks the plate tectonics we see on our planet, instead forming these unique circular features. Some researchers even propose that coronae might be part of a larger system of crustal movement, where the planet's surface is constantly being reshaped by internal forces. Despite the progress we've made in understanding coronae, many questions remain. Why do some coronae have such intricate patterns while others are simpler? Are they all formed by the same processes, or do different mechanisms create these structures? And perhaps most importantly, what do coronae tell us about Venus's past and present geological activity? Each discovery brings us closer to answering these questions, but for now, coronae remain one of the planet's most fascinating mysteries. As we continue to unravel the secrets of Venus's surface, let's turn our attention to another peculiar feature: the spider-like arachnoids. What are these strange formations and how do they fit into the larger picture of Venus's geology? Stay with us as we explore this next chapter in the story of our mysterious neighbor. Now, let's shift our focus to another one of Venus's most bizarre and captivating features, the arachnoids. These spider-like formations, scattered across the planet's surface, are unlike anything we've seen on Earth or any other planet in our solar system. Named for their resemblance to a spider's web, arachnoids are characterized by a central point surrounded by a network of radial fractures that extend outward, creating a striking and intricate pattern. But what exactly are these features and how do they form? Arachnoids are believed to be the result of volcanic and tectonic activity, though their exact origins remain a mystery. Scientists think that these structures might form when magma pushes up from beneath Venus's crust, causing the surface to crack and fracture in a radial pattern. The central point of an arachnoid could be the site of a volcanic vent or a collapsed dome, while the surrounding fractures might be caused by the crust stretching and breaking as the magma rises. This process is somewhat similar to how coronae form, but arachnoids have a much more distinct and web-like appearance, making them stand out as a unique geological phenomenon. What makes arachnoids particularly fascinating is their size and complexity. Some of these features can span hundreds of kilometers, with fractures extending far beyond the central point. The intricate patterns suggest that the forces shaping Venus's surface are both powerful and precise, creating features that are as beautiful as they are mysterious. Unlike Earth, where tectonic plates move and interact in predictable ways, Venus's crust seems to behave differently, allowing for the formation of these spider-like structures. One of the most intriguing aspects of arachnoids is their connection to Venus's volcanic activity. Many of these features are found near regions with active or recent volcanic activity, suggesting that they might be a byproduct of the planet's internal heat and geological processes. Some researchers even speculate that arachnoids could be evidence of ongoing volcanic activity on Venus, hinting that the planet might still be geologically active today. If true, this would challenge our understanding of Venus as a dormant world and open up new questions about its interior dynamics. But arachnoids aren't just about volcanoes, they also reveal something about Venus's crust. The way these features form suggests that the planet's crust might be more brittle and prone to fracturing than Earth's. This could explain why Venus lacks the plate tectonics we see on our planet, instead forming these unique radial patterns. Some scientists propose that arachnoids might be part of a larger system of crustal deformation, where the surface is constantly being reshaped by internal forces. This idea aligns with what we've seen with coronae and other features, painting a picture of a planet with a dynamic and ever-changing surface. Despite the progress we've made in studying arachnoids, many questions remain. Why do these features have such a distinct spider-like appearance? Are they all formed by the same processes, or do different mechanisms create these structures? And what do arachnoids tell us about Venus's geological history and present-day activity? Each discovery brings us closer to answering these questions, but for now, arachnoids remain one of the planet's most enigmatic features. As we continue to explore the mysteries of Venus, let's turn our attention to another intriguing phenomenon, the faint blue halo sometimes observed around the planet. What causes this mysterious glow, and what does it reveal about Venus's atmosphere? Stay with us as we uncover the secrets of this next chapter in the story of our mysterious neighbor. Now, let's turn our gaze to one of Venus's most ethereal and elusive mysteries, the faint blue halo that occasionally surrounds the planet. This ghostly glow, often described as a soft, bluish ring encircling Venus, has captivated astronomers and skywatchers for centuries. But what exactly causes this phenomenon, and what secrets does it hold about the planet's atmosphere? The blue halo is most commonly observed during twilight, when Venus is low on the horizon and the sun's light is scattered through Earth's atmosphere. Some scientists believe that the halo is the result of sunlight interacting with Venus's thick atmosphere, specifically its sulfuric acid clouds. As sunlight passes through these clouds, it scatters in a way that creates a bluish tint, similar to how Earth's sky appears blue due to the scattering of sunlight by nitrogen and oxygen molecules. This theory suggests that the blue halo is essentially a byproduct of Venus's unique atmospheric composition and the way it interacts with light. However, not all researchers are convinced that scattering alone explains the blue halo. Another intriguing theory points to the possibility of atmospheric phenomena, such as auroras or airglow, playing a role. On Earth, auroras occur when charged particles from the sun interact with our magnetic field, creating colorful displays in the sky. While Venus lacks a global magnetic field, it does have localized magnetic anomalies that could potentially produce similar effects. Additionally, airglow, a faint emission of light caused by chemical reactions in the upper atmosphere, might contribute to the halo's glow. These reactions could release energy in the form of blue light, adding to the mysterious aura surrounding Venus. One of the most fascinating aspects of the blue halo is its rarity and unpredictability. Unlike other atmospheric phenomena, such as Venus's sulfuric acid clouds or its super-rotating winds, the blue halo is not always visible. This has led some researchers to speculate that it might be linked to transient events, such as volcanic eruptions or solar storms, which could temporarily alter the planet's atmosphere and create the conditions necessary for the halo to appear. If true, this would make the blue halo not just a beautiful curiosity, but also a potential indicator of Venus's dynamic and ever-changing environment. Despite the progress we've made in understanding Venus's atmosphere, the blue halo remains a puzzle. Is it purely a result of light scattering, or does it hint at deeper atmospheric processes at work? Could it be a combination of factors, including volcanic activity, magnetic anomalies, and chemical reactions? Each observation brings us closer to unraveling this mystery. But for now, the blue halo continues to shimmer as one of Venus's most enigmatic features. As we move forward in our exploration of Venus's mysteries, let's shift our focus to another captivating phenomenon: the massive waves detected in the planet's atmosphere. What causes these enormous atmospheric disturbances, and what do they tell us about Venus's weather patterns? Stay with us as we dive into the next chapter of this fascinating journey. Now, let's journey into the swirling skies of Venus to uncover another of its atmospheric enigmas: the colossal waves that ripple through its dense atmosphere. These massive disturbances, often compared to ocean waves, stretch for thousands of kilometers and have left scientists scratching their heads. What could possibly create such enormous waves in a planet's atmosphere, and what do they reveal about Venus's turbulent weather systems? The giant waves in Venus's atmosphere were first detected by spacecraft observations, revealing patterns that seem to defy expectations. Unlike Earth's atmospheric waves, which are typically smaller and more localized, these Venusian waves are immense, sometimes spanning the entire planet. One leading theory suggests that these waves are caused by the interaction between Venus's super-rotating atmosphere and its surface features. As the atmosphere whips around the planet at incredible speeds, 60 times faster than the surface, it may collide with mountain ranges or other topographical obstacles, creating ripples that propagate upward into the atmosphere. This process, known as mountain wave generation, is similar to how ocean waves form when wind blows over water, but on a planetary scale. Another intriguing possibility is that these waves are driven by temperature differences in Venus's atmosphere. The planet's thick clouds trap heat, creating extreme temperature gradients between the day and night sides. These stark contrasts could generate atmospheric waves as the hot air rises and cooler air sinks, setting off a chain reaction of massive oscillations. Some researchers even speculate that these waves might play a role in maintaining Venus's superrotation, acting as a kind of atmospheric engine that keeps the winds moving at such astonishing speeds. But what makes these waves truly baffling is their sheer size. On Earth, atmospheric waves are typically limited by the planet's relatively thin atmosphere and strong gravitational pull. Venus, however, has an atmosphere so dense that it behaves almost like a fluid, allowing waves to grow to extraordinary proportions. This unique environment might explain why the waves on Venus are so much larger than anything we see on our own planet. Yet, even with this explanation, the exact mechanisms behind their formation and persistence remain unclear. Some scientists have proposed that these waves could also be linked to Venus's mysterious, Y-shaped cloud patterns or even its polar vortices, suggesting a complex interplay of atmospheric phenomena. Could these waves be a key to understanding how Venus's atmosphere maintains its chaotic yet strangely stable state? Or do they hint at deeper, unseen processes occurring beneath the planet's thick cloud cover? Each new observation brings us closer to answers, but for now, these giant waves remain one of Venus's most captivating mysteries. As we continue to unravel the secrets of Venus's atmosphere, let's turn our attention to another intriguing phenomenon, the faint glow known as night glow that illuminates the planet's dark side. What causes this eerie light, and what does it tell us about Venus's atmospheric chemistry? Stay with us as we explore the next chapter in this journey through the mysteries of our enigmatic neighbor. Now, shifting our gaze to the dark side of Venus, we encounter a phenomenon as eerie as it is fascinating, the mysterious night glow. Unlike the bright, sunlit side of the planet, Venus's night side is cloaked in darkness, yet it isn't completely devoid of light. A faint, ghostly glow has been observed illuminating the planet's shadowed hemisphere, leaving scientists intrigued by its origins and implications. This glow, known as night glow, is not unique to Venus. Similar phenomena have been observed on Earth and Mars, but on Venus it takes on a particularly enigmatic character. The glow is thought to be caused by chemical reactions occurring high in the planet's atmosphere. When sunlight interacts with Venus's atmosphere during the day, it breaks apart molecules like carbon dioxide and nitrogen, creating highly reactive atoms and ions. As these particles drift to the night side, they recombine, releasing energy in the form of light. This process, known as chemiluminescence, is similar to the way glow sticks emit light through chemical reactions. However, the night glow on Venus isn't uniform or constant. It appears in patches and varies in intensity, suggesting that the chemical processes driving it are influenced by the planet's complex atmospheric dynamics. For instance, the super-rotation of Venus's atmosphere, where winds whip around the planet at incredible speeds, could play a role in transporting these reactive particles to the night side, creating localized areas of glowing light. Some researchers also speculate that the night glow might be linked to Venus's mysterious ashen light, a faint illumination observed by astronomers for centuries, though the exact connection remains unclear. What makes Venus's night glow particularly puzzling is its unpredictability. Unlike Earth's auroras, which are driven by interactions with the solar wind and can be forecasted, Venus's night glow seems to follow its own rules. This unpredictability has led scientists to wonder whether other factors, such as volcanic activity or even unknown atmospheric chemistry, might be contributing to the phenomenon. Could the night glow be a window into processes occurring deep within Venus's atmosphere or even on its surface? Or does it hint at a more intricate interplay of chemical and physical forces than we currently understand? As we continue to study this faint glow, it serves as a reminder of how much we still have to learn about Venus. Each observation brings us closer to unraveling the secrets of its atmosphere. But for now, the night glow remains a captivating mystery, illuminating the dark side of our enigmatic neighbor in more ways than one. Next, we'll explore another of Venus's puzzling features, the craters that seem to defy expectations by lacking the debris fields typically seen around impact sites. What could explain these craters without ejecta, and what do they reveal about Venus's surface and history? Stay with us as we delve deeper into the mysteries of this fascinating planet. Now, let's turn our attention to one of Venus's most perplexing geological mysteries, the craters that seem to defy the rules of planetary science. On most planets, when a meteor strikes the surface, it creates a crater surrounded by a field of debris known as ejecta. This material is blasted outward by the force of the impact, leaving a telltale ring of scattered rocks and dust. But on Venus, some craters are missing this signature feature, leaving scientists scratching their heads. Why do these craters lack ejecta, and what does this tell us about Venus's unique environment? One leading theory points to Venus's thick, dense atmosphere as the culprit. When a meteor enters Venus's atmosphere, it encounters resistance far greater than on planets like Mars or the Moon. The atmosphere acts like a brake, slowing the meteor down and potentially causing it to disintegrate before it even reaches the surface. This could result in less forceful impacts, producing craters without the usual debris fields. Additionally, the extreme heat and pressure on Venus's surface might cause any ejected material to quickly erode or melt, effectively erasing the evidence of the impact over time. Another possibility is that Venus's surface is unusually smooth and resilient. Unlike Earth, which has active plate tectonics and erosion processes that constantly reshape its surface, Venus appears to have a more static crust. Some scientists suggest that the planet's surface may have been resurfaced by massive volcanic activity in the past, creating a hardened layer that resists the formation of ejecta. This could explain why some craters look so clean and well-defined, as if the surface simply absorbed the impact without scattering debris. But there's another twist to this mystery. Some researchers propose that Venus's atmosphere might actually redistribute ejecta in ways we don't fully understand. The planet's super-rotating winds, which whip around Venus at incredible speeds, could carry ejected material far from the impact site, effectively hiding it from view. This would make it seem as though the craters have no ejecta, when in reality, the debris has simply been blown away or buried under layers of volcanic material. The absence of ejecta around these craters isn't just a curiosity, it's a clue to understanding Venus's geological and atmospheric history. By studying these unusual features, scientists hope to uncover more about the planet's surface composition, its volcanic activity, and even the role its atmosphere plays in shaping its landscape. Each crater without ejecta is a puzzle piece, helping us piece together the story of how Venus became the enigmatic world we see today. As we continue to explore Venus's mysteries, let's move on to another intriguing feature: the massive rift zones that stretch across its surface. What do these giant cracks reveal about Venus's tectonic activity, and how do they compare to similar features on Earth? Join us as we dive deeper into the secrets of this fascinating planet. Now, shifting our focus to another striking feature of Venus, let's explore the massive rift zones that stretch across its surface. These enormous cracks, some spanning thousands of kilometers, are reminiscent of Earth's mid-ocean ridges, where tectonic plates pull apart and create new crust. But on Venus, the story is far more mysterious. What causes these rift zones, and what do they tell us about the planet's tectonic activity, or lack thereof? Unlike Earth, Venus doesn't have the same system of moving tectonic plates. Instead, its surface appears to be a single, rigid shell. So, how do these rift zones form? One leading theory suggests that Venus's crust is being stretched and pulled apart by forces deep within the planet. As the crust thins and cracks, it creates these massive valleys, some of which are several kilometers deep. This process, known as rifting, could be driven by the planet's internal heat, which causes the crust to expand and fracture over time. But here's where things get even more intriguing. Some of these rift zones are associated with volcanic activity, hinting that Venus's interior might still be active. Lava flows and volcanic domes have been observed near these cracks, suggesting that molten rock from beneath the surface is pushing its way up, further widening the rifts. This raises the possibility that Venus isn't as geologically dead as we once thought. Could these rift zones be evidence of ongoing tectonic or volcanic processes? Another fascinating aspect of Venus's rift zones is their sheer size. Some of these features are larger than anything found on Earth, stretching across vast regions of the planet's surface. This suggests that the forces at work on Venus are far more intense than those shaping our own planet. The lack of plate tectonics might actually amplify these forces, as the rigid crust resists movement until it finally gives way, creating these dramatic fractures. Studying these rift zones isn't just about understanding Venus, it's about uncovering the broader story of how rocky planets evolve. By comparing Venus's rift zones to Earth's mid-ocean ridges, scientists can gain insights into the different ways planets release internal heat and reshape their surfaces. Each crack and valley on Venus is a window into the planet's geological history, offering clues about its past and present activity. As we continue to unravel the mysteries of Venus, let's turn our attention to another puzzling feature: the bright patches scattered across its surface. What causes these reflective areas, and what do they reveal about the planet's composition? Join us as we delve deeper into the secrets of this enigmatic world. Now, let's turn our attention to one of the most visually striking mysteries of Venus: the bright patches scattered across its surface. These reflective areas stand out dramatically against the planet's otherwise dark and rugged terrain, sparking curiosity about what they could be. Unlike the rest of Venus's surface, which is largely covered in volcanic plains and ancient lava flows, these bright patches reflect significantly more light, making them a focal point for scientists trying to decode the planet's secrets. So, what exactly are these bright patches? One leading theory suggests they could be composed of highly reflective minerals, such as pyrite or certain types of metallic compounds. These materials, often referred to as fool's gold on Earth, have a natural ability to reflect light, which could explain why these areas appear so luminous. Another possibility is that the patches are made up of freshly exposed rock, perhaps from recent volcanic activity or tectonic shifts. When lava cools and solidifies, it can form smooth, glassy surfaces that reflect light more effectively than older, weathered terrain. But the mystery deepens when we consider how these patches formed. Some scientists propose that they could be remnants of ancient volcanic eruptions, where lava flows created large, flat plains that have since been preserved. Others speculate that these bright areas might be the result of chemical reactions between Venus's surface and its thick, sulfuric acid-laden atmosphere. Over time, these interactions could have altered the surface composition, creating patches of highly reflective material. Interestingly, the distribution of these bright patches isn't random. They often appear near regions of volcanic activity or tectonic deformation, hinting at a possible connection between these features and Venus's internal processes. Could these patches be evidence of ongoing geological activity, or are they simply relics of a more turbulent past? The answer remains elusive, but each new observation brings us closer to understanding their true nature. What makes these bright patches even more fascinating is what they reveal about Venus's surface dynamics. By studying their composition and distribution, scientists can gain insights into the planet's geological history and the forces that continue to shape it. Are these patches a sign of recent volcanic eruptions, or do they point to a completely different process at work? The more we learn, the more questions arise, keeping Venus firmly in the spotlight as one of the most enigmatic worlds in our solar system. As we continue to explore the mysteries of Venus, let's shift our focus to another puzzling feature: the planet's surprisingly low number of impact craters. Why does Venus have fewer craters than expected, and what does this tell us about its geological activity? Stay with us as we uncover the secrets behind this intriguing phenomenon. Now let's dive into one of the most perplexing aspects of Venus: its surprisingly low number of impact craters. For a planet of its size and age, Venus should be covered in craters, much like the Moon or Mercury. Yet when we look at its surface, we find far fewer than expected. This raises a critical question: where did all the craters go? The answer lies in the planet's unique geological processes, which have reshaped its surface over time. One of the leading theories to explain this mystery is volcanic resurfacing. Venus is home to some of the most extensive volcanic activity in the solar system. Massive lava flows could have buried older craters, effectively erasing them from view. Imagine a planet-wide flood of molten rock, covering vast stretches of terrain and smoothing out the scars left by ancient impacts. This process, known as global resurfacing, might have occurred in a relatively short period, geologically speaking, wiping out much of the evidence of past collisions. But volcanic activity isn't the only suspect. Tectonic forces could also play a role in Venus's surface renewal. Unlike Earth, Venus doesn't have plate tectonics in the same way, but it does experience significant crustal deformation. The planet's surface is marked by vast rift zones, mountain belts, and other features that suggest its crust has been stretched, compressed, and reshaped over time. These tectonic processes could have disrupted or erased craters, further contributing to their scarcity. Another intriguing possibility is that Venus's thick atmosphere acts as a shield, breaking up smaller meteoroids before they can reach the surface. While this wouldn't explain the absence of larger craters, it could account for why smaller impacts are less common. Combined with volcanic and tectonic activity, this atmospheric filtering might help explain why Venus's surface appears so young and relatively unmarked compared to other rocky planets. The mystery of Venus's missing craters isn't just about counting holes in the ground. It's about understanding the planet's geological history and the forces that continue to shape it. If Venus experienced a catastrophic resurfacing event, when did it happen? Was it a single planet-wide event or a series of smaller episodes? And what does this tell us about the planet's interior and its ability to generate heat and activity over billions of years? As we piece together these clues, one thing becomes clear: Venus is far from a static, unchanging world. Its surface tells a story of dynamic processes, from volcanic eruptions to tectonic upheavals that have reshaped it time and time again. And while the missing craters remain a mystery, they offer a tantalizing glimpse into the planet's turbulent past and its ongoing evolution. With this in mind, let's explore another layer of this mystery: how the absence of craters challenges our understanding of planetary evolution and what it might reveal about Venus's potential for recent geological activity. Stay with us as we uncover more secrets of this enigmatic world. Now, let's take a closer look at what Venus's missing craters mean for our understanding of planetary evolution. The scarcity of impact craters on Venus isn't just a curious observation, it's a puzzle that forces us to rethink how planets age and change over time. On most rocky worlds like Earth or Mars, craters serve as a kind of historical record, marking the passage of time and the frequency of cosmic collisions. But Venus, with its surprisingly smooth surface, seems to defy this pattern. This raises a critical question: is Venus an exception, or does it reveal something fundamental about how planets evolve? One of the most striking implications of Venus's missing craters is the possibility that the planet underwent a dramatic resurfacing event relatively recently in its history. If true, this would suggest that Venus is far more geologically active than we once thought. Imagine a world where the entire surface is periodically reshaped by massive volcanic eruptions or tectonic upheavals, effectively erasing the scars of past impacts. This kind of activity would challenge the traditional view of planetary aging, where older surfaces are expected to be more heavily cratered. Instead, Venus might be showing us that some planets can reset their surfaces, erasing their history in a geological blink of an eye. This idea also has profound implications for how we study other planets, both within our solar system and beyond. If Venus can undergo such dramatic resurfacing, could other rocky planets do the same? Could there be worlds out there that, like Venus, hide their true age beneath a veneer of fresh lava flows or tectonic activity? These questions push us to reconsider our assumptions about planetary surfaces and the forces that shape them. Venus, in this sense, isn't just a mystery, it's a window into the diverse ways planets can evolve. Another fascinating angle is what Venus's missing craters tell us about its internal heat and geological activity. On Earth, plate tectonics and volcanic activity are driven by the planet's internal heat, which slowly escapes through the crust. Venus, lacking plate tectonics as we know them, must release its heat in other ways. The planet's extensive volcanic features and tectonic deformations suggest that it has found its own unique way to manage this heat, possibly through episodic resurfacing events. This raises the possibility that Venus's interior is still hot and active, capable of driving large-scale geological changes even today, but the implications don't stop there. Venus's missing craters also challenge our understanding of how planets interact with their environments. For example, its thick atmosphere plays a crucial role in shielding the surface from smaller impacts, but it also contributes to the planet's extreme greenhouse effect. This interplay between atmosphere, surface, and interior processes highlights how interconnected planetary systems can be. Venus reminds us that a planet's history isn't just written in its rocks, it's shaped by a complex dance of forces, from the depths of its core to the edge of its atmosphere. As we continue to explore Venus, each new discovery adds another piece to the puzzle. The missing craters aren't just a curiosity, they're a clue to understanding the planet's dynamic nature and its place in the broader story of planetary evolution. And as we uncover more about Venus, we're not just learning about one world, we're gaining insights that could reshape our understanding of planets everywhere. So, what does this mean for the future of planetary science? Let's keep exploring as we delve deeper into the mysteries of Venus. Now, let's turn our attention to one of the most compelling explanations for Venus's missing craters, the role of volcanic activity. Volcanism isn't just a side note in Venus's story, it's a central player in shaping the planet's surface and, possibly, erasing its history. The idea here is that Venus might have experienced massive volcanic eruptions that covered vast areas of its surface, effectively burying older craters under layers of fresh lava. This process, known as resurfacing, could explain why Venus appears so smooth compared to other rocky planets. The evidence for this theory is striking. Venus is home to some of the largest volcanic structures in the solar system, including vast lava plains and towering shield volcanoes. These features suggest that the planet has been geologically active on a grand scale. Some scientists estimate that Venus may have undergone a global resurfacing event around 500 million years ago, a relatively recent time in geological terms. During this event, it's thought that volcanic activity surged, flooding the surface with lava and resetting the planet's geological clock. This would mean that most of the craters we see today are relatively young, while older ones have been erased. But not everyone is convinced. Critics of the volcanic resurfacing theory point out that while Venus has plenty of volcanic features, there's no direct evidence of a single planet-wide event. Instead, they argue that volcanic activity on Venus might have been more gradual, with smaller eruptions occurring over a longer period. This would mean that while volcanism has played a role in shaping the surface, it might not fully account for the scarcity of craters. Additionally, some researchers suggest that other processes like tectonic deformation or even atmospheric erosion could have contributed to the planet's smooth appearance. Another intriguing angle is the possibility that Venus's volcanic activity isn't just a thing of the past. Some scientists believe that the planet could still be volcanically active today. Recent studies have identified regions on Venus that appear to be hotter than their surroundings, hinting at ongoing volcanic processes. If true, this would mean that Venus isn't just a relic of ancient eruptions, it's a dynamic world that continues to reshape itself. This idea adds another layer of complexity to the mystery of its missing craters, suggesting that the planet's surface might still be evolving. So, where does this leave us? While volcanic activity is a strong contender for explaining Venus's smooth surface, it's not the only possibility. The debate highlights the challenges of studying a planet shrouded in thick clouds and extreme conditions. Each piece of evidence brings us closer to understanding Venus, but it also raises new questions. What's clear is that Venus's missing craters aren't just a quirk, they're a clue to the planet's dynamic and possibly ongoing geological activity. As we continue to explore this enigmatic world, we're not just uncovering its secrets, we're rethinking what we know about how planets evolve, and that's a mystery worth pursuing. Now, let's take a closer look at the tantalizing possibility that Venus might still be geologically active today. While much of the evidence points to ancient volcanic activity reshaping the planet's surface, there's growing interest in whether Venus continues to rumble and erupt beneath its thick, sulfuric clouds. This idea isn't just speculative, it's supported by intriguing clues that suggest Venus might still be a dynamic world, far from the dormant planet some once imagined. One of the most compelling pieces of evidence comes from observations of Venus's surface temperature. Certain regions appear to be significantly hotter than their surroundings, hinting at heat sources that could be linked to ongoing volcanic activity. These hotspots, detected by spacecraft like the European Space Agency's Venus Express, raise the possibility that magma might still be flowing or even erupting on Venus today. If true, this would mean that Venus isn't just a relic of its volcanic past, it's a planet that's actively reshaping itself, even now. Adding to this mystery are the unusual surface features that seem to defy easy explanation. For instance, some areas on Venus show signs of recent deformation, with cracks and ridges that suggest the planet's crust is still moving and shifting. These features, combined with the scarcity of craters, point to a surface that's being continuously renewed, possibly through volcanic or tectonic processes. It's as if Venus is constantly erasing its own history, leaving behind only the freshest geological scars. But what could be driving this potential activity? One theory suggests that Venus's interior might still be hot enough to fuel volcanic eruptions, despite its lack of plate tectonics. Unlike Earth, where tectonic plates constantly recycle the crust, Venus might release its internal heat through massive, episodic eruptions. These events could cover large areas with lava, effectively resurfacing the planet and wiping away older features like craters. If this is the case, Venus might be experiencing a slow but steady geological heartbeat, pulsing with activity over millions of years. Of course, not everyone is convinced. Some scientists argue that the evidence for recent activity is still circumstantial, and that Venus's surface might simply be preserving the remnants of ancient events. Without direct observations of an eruption or fresh lava flows, it's hard to say for certain whether Venus is still active. But the possibility is too intriguing to ignore, and it's one of the key reasons why future missions to Venus are so eagerly anticipated. By studying the planet up close, we might finally get the answers we need to solve this enduring mystery. So, what does this mean for our understanding of Venus? If the planet is still geologically active, it would challenge our assumptions about how rocky planets evolve over time. Venus could be a rare example of a world that's managed to retain its internal heat and activity, even without the mechanisms that drive Earth's geology. This would make Venus not just a fascinating object of study, but also a key to understanding the diversity of planetary processes across the solar system. As we wrap up this section, it's clear that Venus's potential for recent geological activity adds another layer of intrigue to its many mysteries. Whether it's through volcanic eruptions, tectonic shifts, or some other process, Venus continues to surprise us with its complexity. And as we prepare to explore this enigmatic world in greater detail, one thing is certain: the story of Venus is far from over. As we reach the end of our journey through the 25 unexplained mysteries of Venus, it's impossible not to be struck by just how much this enigmatic planet defies our expectations. From its runaway greenhouse effect and super-rotating atmosphere to its missing water, strange lightning, and mysterious dark streaks, Venus continues to baffle scientists and space enthusiasts alike. Each mystery we've explored, whether it's the absence of plate tectonics, the peculiar pancake volcanoes, or the unexplained brightness of its surface, challenges our understanding of how planets form, evolve, and function. Venus isn't just Earth's so-called evil twin. It's a world that forces us to rethink the very foundations of planetary science. What makes these mysteries so compelling is how they intertwine. The lack of a global magnetic field, the bizarre double vortex at its poles, and the unexplained ashen light phenomenon all hint at processes we're only beginning to grasp. Even the planet's slow rotation and the mysterious hotspots on its surface raise questions about its internal dynamics and geological activity. And let's not forget the strange coronae, arachnoids, and rift zones that dot its landscape, each one a puzzle waiting to be solved. Venus is a planet that refuses to fit neatly into our existing models, and that's what makes it so fascinating. But perhaps the most exciting part of all this is that we're just scratching the surface. Future missions to Venus like NASA Veritas and Da Vinci Plus, as well as the European Space Agency's Envision, promise to shed new light on these mysteries. With advanced instruments and closer observations, we may finally uncover the secrets behind Venus's missing craters, its sulfuric acid clouds, and the massive waves in its atmosphere. Each discovery could rewrite the textbooks and deepen our understanding of not just Venus, but all rocky planets in the universe. So, what do you think? Which of these 25 mysteries intrigues you the most? Is it the possibility of recent geological activity, the strange Y-shaped cloud patterns, or the faint blue halo that sometimes surrounds the planet? Let us know in the comments below. We'd love to hear your thoughts. And if you're as captivated by the mysteries of space as we are, don't forget to hit that subscribe button and ring the notification bell. There's so much more to explore, from the secrets of Mars to the wonders of distant galaxies. Thanks for joining us on this journey through the mysteries of Venus, and we'll see you in the next video.